Okay, so part 1 of homework 3-3 here. So first question says the block in the diagram above is on an air cushion, so they are trying to say there's little to no friction. It is pushed to the right with a force that remains constant from 0 to 1, and then from 1 to 2 the size of the force steadily decreases, right? The thing to watch out for this one, right? It does tell me that the force is decreasing, but it doesn't say that the force is changing direction. And so because of that, even though that force is getting weaker and weaker, my force and therefore my acceleration are still directed to the right. And so this object is going to do the same thing the entire time, right? The object is going to speed up the entire time of the motion. Okay, so option C is my best choice. It speeds up from 0 to 1 and then continues to speed up from 1 to 2. Now it will speed up by less and less and less as that force weakens, but it will still continue to speed up as long as that force is still traveling in the off to the right here. Right, so even though it decreases until it's half its initial value, it's still moving to the right and we're still speeding up. Question 2 here, obviously a big concept we dealt with in that last section, but hopefully one that's not too bad, right? Terminal speed, again, the big key here is the terminal speed happens when the drag force is equal and opposite to the force due to gravity. So just make sure you watch out for the distractors in here, right? So it's not necessarily equal to g. His acceleration is not equal to g because if these two forces were equal and opposite, his acceleration would be 0. So his acceleration is definitely not g. The force of air drag on him is 0. Again, that's not true because then he would be accelerating downward. Really, A and B are the same option. The force of air drag on him is equal to g. This is probably the best distractor in here because the force of air resistance, the force of drag, is not equal to g. The force of drag would be equal to mass times g. Right? The acceleration of the drag would be equal to g, but not the force. Okay, so just watching the phrasing there, because we know a force is a mass times acceleration, you can't have mass times acceleration be equal to an acceleration. That doesn't really make any sense. And then D hopefully wasn't too bad. His speed is not g, right? But option E, the force of the air resistance, the force of the drag is equal to his weight. So the force of the drag is equal to the force of gravity. That is obviously the relationship that's true for us. So the trickiest part about question 2 is just not getting distracted by the other faulty options there. Okay, so question 3 here is a little bit tricky maybe at first. Hopefully not terribly bad though. Here's the right answer, so if you got that right, feel free to jump ahead. For those of us that want to look at this, so we've got our truck parked on the hill here. We know that the truck's force of gravity would be pulling straight down, but they really just asked me how big is the frictional force exerted on the truck if the static coefficient of friction is 0.90. Well, if I want to find the frictional force, right, if I want to find the frictional force, I'm thinking the static frictional force would be equal to my coefficient of static friction times the normal force. The only thing I have to be careful about here is the static frictional force is not necessarily equal to the coefficient times the normal force, right? The static the static frictional force is less than or equal to this value, right? This is the maximum value that static friction could be. So solving for the static friction, I've got my coefficient. I can find my normal force. Now my normal force in this case, right, hopefully we're pretty comfortable with this, but my normal force would come from the cosine component of gravity. So it would come from mass times gravity times cosine of that angle, right, based on this angle here. So that's where I'm going to plug in my numbers. So 4,000 for the mass, gravity obviously being 9.8, and then cosine of my angle of 15. Right, so again, hopefully that's not too bad. If you do have questions on that, feel free to let me know. But I will assume that most of us are comfortable breaking that up. But anyway, when I solve for this, so again, this would represent the maximum static frictional force. When I solve for this number ends up being about 34,077 or 78, I guess if we round that off. Right? So this is the maximum that static frictional force could be. And so probably the most common misanswer I would see on this one would be us just writing this down and then saying that's good. But the problem in this case is I don't necessarily need that full static friction. So I know that static friction could go up to this point if necessary, but I might not need that much. And in fact, if I look at the sine component of my gravity, so if I look at mass times gravity times sine of theta, which is the only force pulling down the incline, friction, right, if the object is parked, if it's not moving, friction and that coefficient going, that component, excuse me, going down the ramp would have to be equal and opposite. So if I find my sine component of gravity, if I do my mass of 4,000 again, times the gravity of 9.8 times sine of 15, I actually find out that this component of gravity is only 10,145, or 10,145.7, I guess, if I've not rounded it off at all, right? Or not rounded it off very much, I should say. So anyway, this is the component of gravity pulling down the ramp. Friction can go up to 34,078, but since it only needs to counteract this, friction will only counteract that. It will only reach that part there, right? So friction will not reach the full 34,000. It will only match the 10,145 or 146 if you prefer, that is going down the ramp. And so that's where my correct answer, it is still static friction, but that static friction is only 10,146 if we're rounding it off to a whole number there, or obviously you could round it off a little bit more as well, right? But make sure you don't oversimplify this one too much. Yes, you need to find the maximum static friction, but you also need to compare if that whole friction force is necessary or not. Okay, so question 4 here is the elevator problem we've seen a few times before. Part A, by the way, is 1,035, Part B is 735, and then Part C is 585. So if you've got those correct, parts A, B, and C, feel free to jump ahead, right? But the idea here is if I ask you to find the apparent weight, so that's like when we would do those problems where it would ask how much does the scale read, right? So if you're standing on a scale in the elevator, how much does it read? That's what the apparent weight is looking for. Well, if I want to know what the apparent weight is, I need to know what the acceleration is. Well, I've got a velocity versus time graph. If I want to find the acceleration, right, I need to be comfortable with the fact that the acceleration is the slope of this graph. So if I want to find the apparent weight at 1 second, well, I just need to know what's the slope at 1 second. Well, that's not too bad, right? The slope at 1 second, it is clearly a straight line, where my slope at 1 second would be a rise of 8 over a run of 2, so 8 divided by 2, so my slope would be a positive 4. So that tells me then that my acceleration at 1 second, is 4 meters per second squared. So this is telling me then that the net acceleration of the elevator at 1 second is 4 meters per second squared. So then if I'm setting up my net force formula, right, I'm thinking about what's causing that. Well, in an elevator, right, if I'm accelerating upward, which is what the positive would be implying here, I'm accelerating upward. If I'm accelerating upward, then the only forces that are providing me that net force, that net acceleration, the only forces that contribute to that would be my normal force, or the apparent weight coming from the scale, right, and my force due to gravity pushing down. So if these are the only two forces that are contributing to my net force, then that apparent weight, so I'm going to go ahead and call this the apparent weight, which is again just my normal force, but it is the apparent weight as well, right? That apparent weight has to be greater than the force due to gravity. So the apparent weight minus the force due to gravity would be what's providing me my net force. So the net force is positive because it's going up. The apparent weight is positive because it's also going up. The force of gravity, however, is working against my apparent weight, and that's why it's a negative quantity, right? So I know the net force comes from mass times acceleration. The apparent weight is what I'm looking for, so I'll just call that FA to abbreviate a little bit more. And then the force due to gravity I can find easy enough, right, because I have the mass and I know the acceleration of gravity. So at this point, I know all of the variables except my apparent weight. My mass of 75, my acceleration upward of 4. Again, I don't know the apparent weight, but I know my mass of 75, and I know the acceleration due to gravity of 9.8. So then simply adding this over to the other side, I find out that my apparent weight ends up being 75 times 4 plus 75 times 98, and that's where I got my 1,035 Newton force. Right, and pause for a moment, right, just to think about that and make sure that makes sense. If I'm accelerating upward, does it make sense that this apparent weight would be more than his actual weight of 75 times 9.8? Well, hopefully it does make sense, right? If we've got an acceleration upward, we kind of know intuitively that we're going to weigh a little bit more, or we're going to feel like we weigh a little bit more than we normally would. So then for part B, well, part B is actually the nice part here, because if we look at the graph, right, at 5 seconds, the slope is 0. And so what that tells me then is at 5 seconds, the net acceleration, right, and therefore the net force and the net acceleration are both 0 as well. Well, if the net acceleration is 0, and again the only forces acting are that apparent weight of the scale pushing up and our force of gravity pushing down, right? If the net force and net acceleration is 0, that tells me those two have to be equal and opposite. So in this case, my apparent weight is simply my force due to gravity, or it's equal to my force due to gravity. So my apparent weight would be just the 75 times 9.8, and that's where I got the 735 answer that I did. Right, so again, my apparent weight right there is 735 newtons. Okay, so nothing too crazy for that part. So then hopefully this gives you enough to maybe try C on your own, and obviously feel free to pause the video and try it if you have not yet done so. But finding the acceleration for this, well, I know the acceleration would be negative, right? I know the acceleration would be negative because it's going down. Again, looking at the slope, it goes down 8, it goes over 4. So my acceleration would be negative 2, right? And you could use that acceleration to be negative. What I actually might do, though, is I'm just going to define then, again, for my elevator, I know I've got those same two forces. I'm just going to define the net force, the net acceleration as going downward this time. So my net force, my net acceleration goes downward. So when I'm creating my net force equation, right, my net force is going downward. The force that's going with the net force would be the force due to gravity, and then the force that's going against it would be the apparent weight, right? So if I define my net force here as a positive, then gravity simply is positive as well, and the apparent weight is negative. If I wanted to, I could definitely define the net force as negative, gravity as negative, and the apparent weight as positive. It's going to end up being the exact same thing, right? It's going to be the exact same relationship. So anyway, breaking this up, my mass times my net acceleration of 2 in this case, because I'm accelerating downward at 2 meters per second squared. My force due to gravity, which I already know because I've worked it a couple times now, is 735. And then just solving for the apparent weight. So once again, I know the mass of the person is 75. So solving for the apparent weight, I get 735 minus the 150 that I get from multiplying these two together. So my apparent weight ends up being less, right, than it normally would be. So 585 newtons is what I get for on the trip back down. Okay, so making sure you're comfortable interpreting the graph to help us find the acceleration, because honestly, once you have the acceleration, it's the exact same problem we've done a few times in the past, and hopefully it's not too bad. But obviously, again, if you do have any questions over this, come find me so I can help you out. Okay, so question 5 here has this set up to where I'm pushing downward at an angle of 750. The box is on a flat horizontal surface, and they give me a coefficient of static friction with a box of 0.76. What is the mass of the heaviest box that you would be able to move by exerting this force? Well, in order to determine the heaviest box that I can move, right, I need to figure out what my components are. So if I find the horizontal component of this force, based on the way that I've set it up here, my horizontal component ends up being about 680. I think it's actually 679 point something, but I'll round that off at 680. And then my vertical component here ends up being about 317. Right, again, I'm rounding that off a little bit, but it's close to 317. So the reason it's important to break this up is if I'm able to make the box move, right, I know that as I push to the right and downward, friction would be resisting the motion that I push to the right. So friction is going to be resisting this motion by pushing back to the left. Well, if I want to make the box move, then what that tells me is the static frictional force better be overcome by 680. So again, I need to know that that 680 Newton force that's pushing off to the right is at least slightly greater than the static frictional force, right? So then I'm just going to figure out what the maximum static frictional force is and what the heaviest mass that would give me that force would be, right? So using this relationship, well, the static frictional force is US times the normal force, and the normal force in this case, we do have to be careful, right? We have to realize that the normal force is going to account for both the force of gravity pulling down and this applied force going down. So the normal force pushing up needs to be equal and opposite to both of those measurements. Okay, so the force of gravity plus the 317 newtons. So then really at this point all I'm doing is 680 is greater than my coefficient of 0.76 times my normal force, which again is the force of gravity plus 317. I will show the rest of this worked out in the second part, but hopefully this is enough to get you started.